Okay, so we're on page 460 where it says normal probabilities. Okay, so normal probabilities. A normal probability density function or a normal probability basically is a probability that looks like this. This is a what we call it's normal. This is the what you guys know this as the what? The bell curve, right? This is the bell curve. This is the bell curve, right? This is the bell curve. It's the bell curve where you have in the middle, you have a mean. You have a mean here. Okay, you have a mean. And then a normal probability distribution. The thing that makes this really special is that in a normal distribution, you only need two parameters, and that defines the entire function. And you need to know the mean. What else do you need to know? The sigma, the standard deviation. Okay, these are the two things you need to know. And on page 431, if you know that, you can, it actually gives you the mathematical definition, which AP Stats we've never talked about. So here it is. Sigma square root of 2 pi e to the negative x minus sigma squared over sigma 2 sigma squared. So this is somewhat familiar for those of you who've taken statistics, but really it's not, okay? So this is, so here's the x. The x is really up here. So this is the x, okay? And this is the, what we call the normal probability distribution. You are not going to be required to know this, just letting you know. This is what the normal distribution looks like. Okay. So the sigma, which is the standard deviation. Eva, what is the definition of the standard deviation?
How far it typically varies.
Yeah, so if you pick any point along this normal distribution, if you pick any point, the difference from that point, the distance from that point to the mean on average is called the standard deviation. The larger the standard deviation, the more your graph is going to be flatter, right? It's going to be flatter like this. The smaller the standard deviation, the smaller it's going to be more pronounced like this. Okay. And just for your edification, if you're doing statistics, you want the green one. But it's easier to predict what it's going to be. Okay. All right. Anyway, so let's look at page 431. We have what is called the 68, 95, 99.7 rule. And so this is what we need to know. Not necessarily this. We need to know is the 68, 90, 95, 99.7 rule. And what that rule states is that if I take any normal distribution, and this is mu, and if I go out 1 sigma in both directions, so this guy here would be mu minus sigma, where this guy would be mu plus sigma. If I go from here, straight. I go from here to here, I am guaranteed that I will have 68% of the total population in that plus or minus 1 sigma. Okay. If I go out 2 sigmas, this will be mu minus 2 sigma, mu plus 2 sigma. If I go like this purple region is going to be 95%. We go out one more, it's going to be what? 99.7%, right? 99.7%. And that's exactly what the 68, 95, 99.7 rule means. Okay? So what does this mean? So if I gave you guys a test, and you guys did really poorly, and your average was 80% out of 100, okay, and I told you that the mean was 80% and the sigma was 5, okay, what percent would I have between 75 and 85? Did you get that? You understand what we just said? Because this would be 80, which means that 1 sigma out would be 75, right? 2 sigma outs would be 70. 1 sigma up here would be 85. 1 sigma up here would be 90. Right? So I posed the question, what would be the percentage between 75 and 85? So that's between plus or minus 1 sigma, right? So that would be 68%. If I asked you what was the total percentage between 80 and 85, since this is symmetrical, this is totally symmetrical, what would be between here and here? It'd be 30, it'd be half of this, right? 34%, right? So I have 34% here, 34% here, correct? If I asked you how many people got less than 75, what would that be? So how many got from 75 all the way out here? We know this is 34%. We know from here to here is what percent? 50%. That means that from here to here must have been 16%. Okay, so we're good there? That's 16%. Okay. How many people got above 90? Greater than 90? Since this is 90 right here, right? I know from here all the way to here is what percent? 95%, right? Which means that the other 5% must be on these two tails over here, right? So to be half of that, so yeah, greater than 90 would be 2.5%. Okay, so I can ask really odd questions like what would be between 75 and 90? What would that be? 75 to 90. From here to here was what percent? 68%. So I just need to figure out what from here to here is. Right? So this is, so I look at this as half. This is 34%, correct? What is here to here? Correct. It's half of 95. Right? So it's going to be 47.5% from here to here. But I know from here to here was 34%, correct? So I have to add those two together. 81.5%. Okay. So these are all fair game. When I've asked this kind of question, you know the kind of questions that I can ask associated with that. A lot of times in statistics, you will not, the point that you're trying to find or the reason that you're trying to find are not going to be this clear cut. Okay, you're going to have like 0.25 sigma to negative, I don't know, 0.3 sigma or some stupid stuff like that. Okay. And those we deal with by using Your calculator. The calculator actually has a program that will calculate that stuff. We're not going to go into that today. We're not going to go into that today, but just realize that there is a program. Okay, so let's go and do example number 5. Let's just go straight to example number 6. Example number 6. Suppose a telephone helpline takes a mean of 2 minutes to answer calls. The standard deviation is 0.5. Okay, so again, so on this one, we're going to have the average was 2, and sigma was 0.5. And 68% of the calls are 1.5 to 2.5. And 99.7% of the calls are answered between 0.5 and 3.5 minutes. Assume that the time to answer calls is normally distributed. So what is that? Where's the question? There's no question. All right, forget about that one. Go to example number 7. Suppose that frozen spinach boxes marked as 10 ounces of spinach have a mean weight of 10.3 ounces. So the mean weight is 10.3. So why would you possibly not say 10.3? Huh? Okay. So if you actually, or if you just manufacture it as 10 and you say it's 10, half of the customers could complain, right? And say, you didn't give me 10, you gave me 9 point whatever, right? Okay, so yes, you understate, over deliver type of thing, right? Okay. So there was a standard deviation of 0.2. Standard deviation was 0.2. A, what percentage of all spinach boxes can be expected to weigh between 10 and 11 ounces? Okay, so I'm trying to find from 10 to 11. So what do we get? How many sigmas is 10 away from here? 10.3 minus 10, oops, number 10 minus 10.3 over 0.2, right? Negative 0.3, 0.2, negative 1.5, right? So I'm negative 1.5 sigmas away on this side. On that side, how far am I away? 11 minus 10.3 over 0.2, 0.7, 0.2, 3.5. Now let's go ahead and bring out your calculators. Now in your book, it actually has you do the NINT and actually has you put in the true definition, the normal probability density function. Okay, that's a lot of inputting to do, and it's really complicated. Okay, just look at it. Okay, so I don't want you to do that. What I want you to do is we're going to go to stat calc. Is it second vars? I'm looking for norm CDF.
Yeah.
Second vars. Second vars. Find norm CDF. This is a normal probability distribution, cumulative distribution function. Okay, and we're going to go from 10 to 11, where our mean was 10.3, sigma was 0.2. Put that in, and what do you get? 0.933, which is exactly the same thing that the book got. using the nint of the original function. Okay, all right. So just letting you know that that's a type of thing. B, what percentage would we expect to weigh less than 10 ounces? So less than 10 ounces, right? It's the same thing here, right? I want to go from less than 10 ounces, so we'll just say 0 to 10 ounces, right? 0 to 10 ounces. And the same thing, because this is the lower bound, this is the upper bound. This is the mean, this is a standard deviation. So go ahead and do that. And what do you get? 0.067, everybody got the same thing? 0.067. Get that? So it's approximately 6 to 7% of the time, you're going to actually get one that is less than 10 ounces. Okay, that's pretty good odds because, first of all, how many people are going to actually weigh it? Right? How many people are going to write to you saying that it's less than 10, right? Out of the 6.7%. Okay? So you're pretty well covered there, right? Okay, C, what is the probability that a box weighs exactly 10 ounces? What does that mean? You put 10 and 10, okay, it says 0, right?
If you think about it like an integral,
So think of,
you're going to the same place.
yeah. So you're looking at this one single line, right? In other words, there's no width. There's no width, and that's why it's 0. Does that make sense? So theoretically, it's 0, but realistically, there's got to be one that's 10, right? Actually 10. Correct? So you see the difference there? What does the book say? This would be the integral which is 0. The 0 probability seems to be straight to first, but remember that we are assuming a continuous, unbroken interval of possible spinach weights. And 10 is but one of an infinite number of. So it's basically 1 over infinity, which is 0. Make sense? All right, we're done. We are done with